Hello? Okay. Sorry, I didn't turn the mic on. And from the recording, you might have missed the first part, but it's okay. We still got the second part. Yeah. So, what defines your source and drain is the lowest potential, lowest voltage of the two nodes is your source. All right. Give you another example: 0 volt, 3 volt, 1 volt. Which one is the source? Lowest voltage, 1 volt. Why is that not 0? Yeah, that's your gate. So don't think the lowest all the way. So just compare this and that. The lowest one, the lowest one is your source. All good? Any questions? Yep. That is a very good question. I'm gonna introduce to you, there are 3 modes. Well, at least 3 modes. We don't deal with subthresholds. So 3 modes of a MOSFET. So the first case, easiest case, cut off, which means the transistor is completely off. So it will be an open switch. All right, open switch means that you have a very high impedance between your source and drain. Okay, when will it be cut off? The condition is that VGS minus VT is smaller than 0. That is for your NMOS. So I will go through all the NMOS cases first, and then we'll go to PMOS. Okay, so when VGS is smaller than VT, or smaller, okay, so when your VGS is smaller than your VT, then your transistor is not working, which means you are providing a control voltage to your transistor that is smaller than the threshold voltage. And for example, so this is connected to ground. This is your drain, VD initially equals to 5 volt, okay? And that's your VG. So VGS equals to your VG minus your VS. And this is obviously your source, right? Because it is connected to ground. So let's ignore the body first. Well, because let's ignore the body. Assume the body is connected to ground as well. So for this one, you will have to know what your VT is. VT is defined by the technology. Usually we'll take 0.5, 0.7. It depends on how heavy you're doping your silicon. So it'll be given. And also you can simulate that. So we'll talk about whether this is a constant or not later on. But as first to the first order approximation, we assume it's constant. Okay. Don't get it wrong. It is different from your BJT VTH. VTH is always a constant number, right? But this one depends on technology. So when you are doing your tests again and your questions, make sure you check out what your VT is. Sometimes I like 5.5, sometimes I like 0.3. Don't assume it's always 0.7. Yeah. But for this one, we'll use 0.7 for now. So let's say VT equals to 0.7 volt. So the condition is cut-off region is when VGS minus VT smaller than 0. So VGS minus VG minus your VS minus your VT smaller than 0, right? So we are trying to look what is the VG. So VG is smaller than your VS plus VT. All good. Right now your VS is 0. Yep. So as long as your VG is still smaller than your VT, your transistor is not working. Okay. So this is a very common setup for an NMOS transistor. You try to put your source to ground, and as long as your VG is still smaller than your VT, then it doesn't work. All right, that is the cutoff. Any questions? Nope. All good. So what happens if your VG is greater than your VT? Then it will start working. So for another example, VD equals to VDD, T equals to 0. Your VG, I just give you a huge voltage, VDD. Source is connected to ground. All right. So for this case, is this in cutoff region? No. Why? What is the condition for cutoff region? That's right. So remember, it's VGS, not just VG. Yep. So, but right now the S is 0. So literally, it's just VG greater than your VT. But the thing is, I haven't told you what my VT is. Yep. So if I say my VT is huge as well, then it could be still in cutoff. All right. But usually it's not the case. So say VT equals to 0.7, VDD equals to 2 volt. All right. Then this one will be working. So we have our VGS equals to 2 minus 0, which is 2 volt, which is greater than your 0.7 VT. Then this is operating. And then whenever it operates, what does it mean? So my switch is closed. Okay, so this is drain, this is your source. Okay, so you have a closed switch. And right now, since this is the drain, it is connected to 2 volt. This is source connected to ground, right? And this voltage VD will be discharged. Yes. Oh, I haven't defined it yet. Yep. So whenever it's turned on, let's ignore the subthreshold. Whenever it's turned on, then it can either be linear mode or saturation mode. You can see from the notes. So we'll discuss about the linear mode first. So linear mode happens when VGS minus VT is greater than 0, right? This is the operating case. But also you have a small VDS. Okay, so we will see for this one. Initially, what is your VDS? VDD minus 0 volt, which is VDD. That's huge. VGS equals to VDD as well. So VGS minus VT will be smaller than your VDS in this case, right? So for this case, initially it will be in saturation mode. Yeah, but eventually, because your VDS will drop due to your VD keep being discharged. So assume you have a capacitor here. There will be current flowing through. You have 2 volt, you have a resistor, you have 0. There will be a current flowing through from your drain to your source. Eventually, this will be discharged to what voltage? 0. Yep. So eventually, your VD will become 0 volt. All right. And in this case, 0 volt. That's your VD. That's your VG. In this case, is your transistor still on or off? Off. On. Okay. I need some hands. Who thinks it's on? Show me your hands. On. Who thinks it's off? It's a bit confusing. Why confusing? Yep. A linear mode transistor is an on transistor. Yep, so it is still on. Because again, when you look what region it is, first thing you look is that what is a VGS? Right now, what is a VGS? You have this equals to VDD, which is 2 volt. VGS equals to VDD minus 0 volt, which is VDD, and it's still greater than your VT. So this is not in cutoff. Whenever a transistor is not off, that means it's on. Okay, for at least for this unit. All right. So I've talked about. I've actually talked about both saturation mode and linear mode, but we'll go back to saturation mode. So the condition for, can you guys yell it out? What is the condition for cutoff? Okay, or the other way, we can do this one. Yeah, MOS. What about your linear? Sorry, same, which means same as in cutoff. Okay, VGS minus VT equals to 0, same as in like this. Well, that is the case that you start to turn on the transistor. So when you're having it greater than 0, then your transistor is on. But also there's one more condition. When your VDS is greater than 0. Not exactly, but that could be one of those as well. Yeah, so you're going to compare everything when your transistor is on. So you have your VGS minus your VT. This has to be greater than VDS, and this has to be greater than 0. Okay? Yeah. So saturation is that your VDS is greater than your VGS minus VT, but this is still greater than 0. Okay? So this table summarizes all these things, I think. Okay. Yep. So you can look at this flowchart just to look at the NMOS part. So first thing you check is that whether your VGS is smaller than your VT. Whenever your VGS is smaller than your VT, go straight to off stage. Then you're done because it's off. There's nothing to do. But if your VGS minus VT is greater than 0, then you compare the voltage between your VDS and your VGS minus VT. And if your VDS is kind of small, then you know it's in linear. But if it is kind of large, then it's in saturation. Alright? So it's not too hard, right? NMOS is easy. Yep, question. So that's the pinch-off case, which means that it's somewhere in between. It'll be, if you look at the current, they'll be the same, because it's not like a jumping from one point to another point, so it's continuous. So it's slowly changing from linear to saturation. Yep. And the trouble comes when the PMOS comes. So for PMOS, everything's different, unfortunately. If you don't like to deal with negative numbers, you might struggle a bit, which sometimes is my case too. So bear with me if I confuse you guys. Sometimes I confuse myself. But the good thing about PMOS is that it deals with, one thing is that it deals with VDD. That makes it a bit harder. But if you think about it as the inverted way of an NMOS, that might help you a bit. So let's do the PMOS. That is a PMOS. Oh, sorry. Yes. Okay. So you usually use both. Yep. We will talk about their characteristics. But before that, let's look at the operation. And after you understand these operations, you will know why we will use PMOS, why we will use NMOS. Yes. This is the symbol for PMOS. What's the difference between a PMOS and an NMOS? No, the symbol. Just the symbol itself. Yes. Usually my questions are quite simple, so don't waste time thinking about it too much. All right? There's a circle there. So that helps you to identify whether it's a PMOS or NMOS. All right? That is another symbol for NMOS and PMOS representations, which you'll use it in the lab. But I'll use these one first, and then I'll talk about those ones. So so in digital circuit designs, we usually put it this way. So PMOS, circle, NMOS, no circle. That's it. So similar to an NMOS, it can be a switch. Well, it is a switch. What is the case? So this is still the gate, and this can be source drain source. And tell me what defines the drain and source. Yep, voltage, same as NMOS, voltage. And same as NMOS, they are physically identical, the source and drain. So the voltage, and for your NMOS, what voltage is the source? Highest or lowest? Lowest. Yeah, that's right. But for PMOS, I said everything is inverted. So what defines the source? Highest voltage. Yes, that's right. So assume you have a PMOS like this. This is connected to VDD. This is connected to some kind of VA. This is your VG. Is the upper one the source or the upper one the drain? This one. This one. That is the highest voltage. Yep, that is the source, and that is the drain. Okay? I know it can be confusing. That's why this is a very good example for test questions, I think. And you have to make it very clear, very, very clear. Because if you mix up the source and drain, all your calculations will be wrong. All right? So don't think the top one is always the source or bottom one is always the drain. It doesn't work that way. Remember, always check your voltage. All right? So right now, we compare VGS and VT. All right. The first thing comes. So VT, well, we have VTN, which is the threshold voltage for your NMOS. It's always positive. All right? A common technology. Okay? Don't tell me, nah, some special technology, they have negative VT. Yes, but we deal with the common stuff first. All right? VTN is always positive in our case. And VTP, do you think it's greater or smaller than 0? Yeah, smaller than 0. So that is the worst thing. And VGS, is it positive or negative? Yep, because you can't have anything higher than VDD. So VG minus your VS, now is the case that you have a negative voltage. So you're comparing a negative with negative, which is pretty bad. So how I remember this is that I think about the NMOS. I don't think it's a very good way, but my brain can't process that many things. So I think about the NMOS. So NMOS, this is the case that you have a transistor turning on, right? So for PMOS, it's the other way around. All right? So this is the on case for PMOS. In other words, for PMOS, VGS minus VT is greater than 0. Then what region is it in? Is it on or off? Yep, it's off. Yep, it's off. Okay, so seems like you guys are smarter than me. That's good. So you have to get this clear that whenever I say a PMOS, VGS minus VT greater than 0, then it's off. Which means the switch. Is it an open switch or closed switch? Open switch. No current flows through. Okay, so that is the easiest case. Okay, when it comes to the thing that turns on, you have two modes. Either can I have the names? What mode and what mode? Linear and saturation, right. And in NMOS, try to test your memory. In NMOS, linear NMOS. In linear NMOS, what is the condition? Well, I know it's about VGS minus VT, it's about VDS. So in linear, which one? This one? Yep, all agree? Yep, that is NMOS. And for PMOS, opposite. Yeah, PMOS, linear. VGS minus VT, smaller than VDS. Okay? But in this case, you need to deal with negative voltage. Okay? And obviously, if that is the case, and then saturation, VGS minus VT is... Oh, yeah, that's smart. PMOS. Yep. But provided that your MOSFET is not in off stage. Okay? Clear? So if it goes back to this flow chart, for your PMOS, VT is smaller than 0, and you compare VGS and VT, and if your VGS is greater than your VT, remember, usually your VGS will be negative, and then it's off. Alright? But if it is when it is smaller, then it can be either saturation or linear, and you compare it with VDS. If VDS is greater than your VGS minus VT, then it's linear, and otherwise it's saturation. So, as I said, if you think it can be too confusing, just remember one of those, and then always flip around but don't flip it twice, okay? Sometimes you think, oh, flip it, and then, oh, it's negative. I flip it again, then it's wrong. All right? All clear? All clear? Am I speaking too fast? Okay, good. I try to speak so that when you guys watch the video recording, you don't play like double speed or 3 times speed. Okay, so this is the basic operation of both PMOS and NMOS, and it's about the time to see when we should use NMOS, when we should use PMOS. But before that, do you guys have pen and paper? All have pen and paper? Okay, we'll do something a bit more interesting. Don't look at your notes. Don't look at my screen. Okay. Remember the figure that I said you got to dream about that, which is the cross-section area of your NMOS and PMOS. Okay? Try to draw that out on a piece of paper, on one piece of silicon. So I will give you a piece of silicon. That's your P substrate. Draw your NMOS on this. PMOS on this side. NMOS on this side. Sorry. You are giving a P substrate, and then draw your PMOS here, NMOS here. Okay? You have 2-3 minutes to do it. I'll walk around and see how you go. So when you are done, Under that figure, write out all the conditions for your cutoff, linear, and separation. Okay? Try not to flip through the notes. This is just to test your memory. It doesn't matter if you got it wrong. It will be even better if you got it wrong now, because if you got it wrong now, you won't get it wrong in the tests. Hmm? $5503?
Sorry.
Are you doing 5503? I'll give you 1 more minute. Okay, how does it go? So it tells you, well, one thing is to test out your memory, but also if you face difficulties, it tells you which part you don't understand. All right. So anyone find it a bit difficult when you're trying to draw this one out? Yes.
So does it have to be inside of the envelope?
That's a good question. As far as I remember, no. So if your envelope is far apart from that, then you don't need that to go into the envelope. Yep. Any other things? If you look at your figure, which I saw many people did one mistake, a very common mistake. Compare your figure and this figure. Yep. So your gate has to have a little bit of overlap between your P and this one. Okay? So this is very important because if they're disconnected, well, sometimes for convenience sake, you just draw it straight from the corner, which is not good, which I do that as well. So you'll get marks deducted if you do that. But if it is disconnected, then this gate has no control over your device at all, and your device is not a MOSFET. All right? Anyone miss out the oxide? No? That's good. Anyone miss the metal? Yep, don't miss out the metal. Anyone miss the N-well? So remember it's P, so your figure should be flipped, alright? Should be flipped left and right. So for your NMOS it's N plus P substrate. For your PMOS you need an N-well, P plus, and you need an oxide to isolate them. And, well, even this figure has missed out one thing. Actually 2 nodes. Who can tell me which 2 nodes? Remember your MOSFET is not a 3-terminal device, it's a 4-terminal device. So it has a gate, source, drain, what else? Body, yeah. Where is the body connected? Well, it's not shown here, okay? So ideally, if I'm just drawing the body for your P substrate, well, for PMOS, there will be an M-well, and there, you should have a little bit in your N plus, P plus, P plus, your gate and stuff, and after some distance, you'll have N plus. So this is M-well, and this is the N plus, and then you connect it to the outside world, which is your body, okay? And same for your NMOS, P substrate. One thing, I've seen students put it like this, P plus, and then connect it and say, this is the body. Technically, it's not wrong, but unfortunately, this is unable to be fabricated because you put everything on top of your silicon. You don't put it under, all right? So apparently, the distance between this will be huge compared to your circuit, okay? So you put your P plus here, and then you put your contact, and that's your body. So if you find this figure here, this is just symbolic, okay? So don't think you put the contact underneath your substrate. You actually put it. You will know a bit more when you do your project and your layout, and this is just to give you a preview of what it looks like. All right. Okay. Why don't we take a 10 minutes break, and then when we come back, we'll do some calculations. All right.